The skies are no longer the limit. They're the battleground. And the world's leading powers, China and the US, are locked in a fierce competition to redefine the limits of supersonic flight. Stay with us as we reveal the fastest, most advanced supersonic and hypersonic aircraft taking off in 2025. To understand where we're headed, we need to look back. The story of supersonic flight began decades ago with Concorde, developed jointly by the United Kingdom and France. Concorde was the world's first commercial supersonic airliner, capable of cruising at Mach 2.04, twice the speed of sound. First flown in 1976, Concorde wasn't just fast, it was built to push boundaries. For nearly 3 decades, this plane became an emblem of technological ambition and national pride. The engineering behind Concorde was nothing short of groundbreaking. Its delta wing design, a sharp, triangular configuration, reduced drag while maintaining stability at speeds few dared to imagine. The airframe, crafted from advanced aluminum alloys, could withstand the intense heat generated by friction at 1,250 miles per hour. At these speeds, surface temperatures reached 127 Celsius, causing the aircraft to expand by nearly 10 inches during flight, a challenge engineers overcame with precision and ingenuity. Under its wings, Concorde was powered by 4 Rolls-Royce Snecma Olympus 593 turbojet engines, originally designed for military bombers. These engines provided unmatched thrust, supported by afterburners that ignited raw power to push the plane beyond the sound barrier. Yet this speed came at a cost. Concorde's engines were fuel guzzlers, burning over 25,600 liters per hour. This limited its range to transatlantic flights and priced tickets beyond the reach of most passengers. Only the wealthiest celebrities and diplomats could afford the privilege of flying faster than sound. Concorde was born into an era of fierce geopolitical competition. In the 1960s, France and the UK sought to assert dominance in aerospace innovation, creating Concorde as a declaration of their capability. Meanwhile, the United States wasn't standing idly by. Boeing's 2707 supersonic transport program aimed to eclipse Concorde with an aircraft capable of Mach 3. With its ambitious wing design and significant government backing, the SST project seemed poised to dominate. But America's plans faltered under public and environmental pressure. The sonic boom became Concorde's most significant challenge. Breaking the sound barrier generates shockwaves, a deafening clap that rattled windows and stirred outrage. Public opposition, coupled with the 1973 oil crisis, forced the United States to abandon the SST program in 1971. Leaving Concorde as the lone supersonic airliner. However, even Concorde couldn't escape the boom's limitations. Restricted to transoceanic routes, it was unable to operate overland without causing disruption. This, combined with its immense operating costs, meant Concorde's market was limited. Despite these hurdles, Concorde became a symbol of achievement. It flew passengers from London to New York in under 3.5 hours, shattering the limits of air travel. Its sharp nose, tilting downward during takeoff and landing, was as iconic as its blistering speed. But Concorde's appeal wasn't just its performance, it was a technological marvel that represented an era of relentless pursuit of superiority. Yet every legend faces its reckoning. In 2000, disaster struck. Air France Flight 4590 crashed after takeoff, claiming 113 lives. Investigators found that debris on the runway had punctured a fuel tank, leading to a catastrophic fire. This tragedy, combined with rising maintenance costs and declining demand, forced Concorde into retirement in 2003. Its reign ended, but its legacy endured. Supersonic flight itself is a brutal test of physics and engineering. As speeds approach Mach 1, shockwaves generate immense drag and instability. Concorde overcame these challenges with its delta wings and elongated fuselage, both designed to slice through air at unprecedented speeds. The tilting nose cone, crucial for pilot visibility during takeoff and landing, became a hallmark of its design. These weren't just innovations, they were essential to conquering the sound barrier. The sonic boom, however, remained a persistent adversary. Pressure waves formed at supersonic speeds created an explosive noise that made overland flights politically and socially unacceptable. Environmental studies further revealed that Concorde's emissions at high altitudes contributed to ozone layer depletion, raising questions about the sustainability of supersonic travel. The financial investment in Concorde was colossal. Development costs exceeded $2.8 billion, which is over $15 billion today. a joint expenditure by France and the UK to create a technological masterpiece. Each aircraft cost $23 million to produce, which is equivalent to $140 million today. Airlines operating Concorde faced immense financial pressure, balancing high maintenance and fuel costs against limited profitability. Despite these challenges, Concorde achieved what seemed impossible, bridging continents in record time and setting swift benchmarks that remain unbeaten by commercial airliners. Concorde's influence extended far beyond its own operations. Its development spurred advances in aerodynamics, materials engineering, and propulsion systems. Lessons learned from managing thermal stresses, optimizing fuel efficiency, and refining high-speed stability have shaped modern aviation. Today's engineers stand on the shoulders of Concorde's pioneers, using their insights to develop the next generation of supersonic and hypersonic aircraft. Modern innovators have taken Concorde's legacy and adapted it to the needs of the 21st century. Noise reduction technologies, like NASA's Quiet Supersonic Technology, aim to eliminate the sonic boom. Sustainable aviation fuels promise to reduce environmental impact, while advanced manufacturing techniques streamline production. These advancements address the challenges that once grounded Concorde, bringing the dream of supersonic travel back within reach. Today, the global landscape has shifted. Governments and corporations recognize the strategic value of supersonic flight for both commercial and military applications. Rapid global connectivity and the ability to deploy forces or resources in record time have become critical advantages in an increasingly interconnected world. Investments in supersonic research have surged, driven by the promise of not just faster travel, but greater strategic mobility. In 2025, the race for supersonic excellence has reignited, with new technologies overcoming the challenges of the past. Let's dive into the most ambitious projects shaping this new era. First, Boom Supersonic XB-1 jet. Enter the Boom Supersonic XB-1, a cutting-edge prototype dubbed Baby Boom. Founded in 2014 by Blake Scholl, this remarkable aircraft was created with a singular mission: to bring supersonic travel back to the skies. Scholl's vision is not just about speed, but accessibility. Unlike Concorde, which catered exclusively to the elite, Boom aims to make supersonic flight a viable option for millions of travelers worldwide. The XB-1 jet is a critical step toward achieving this goal, serving as a proving ground for the technologies and designs that will shape the Overture airliner. This ambitious project has attracted over $300 million in investment, supported by high-profile backers like Emerson Collective, American Express Ventures, and Y Combinator. Such robust funding underscores the confidence investors have in Boom's potential to redefine air travel. Designed to cruise at Mach 1.7, over 300 miles per hour, the XB-1 is a sleek, state-of-the-art Yerval. Its development represents a bold leap forward, tackling the challenges of supersonic flight head-on, while leveraging advances in aerodynamics, propulsion, and material science. The aircraft's body is crafted from advanced carbon fiber composites. These materials are lightweight, yet incredibly strong, allowing the XB-1 to withstand the immense forces experienced at supersonic speeds. This structural advantage also contributes to better fuel efficiency, a critical consideration for supersonic travel's economic and environmental viability. The fuselage's sleek and tapered design reduces drag to an absolute minimum, enabling the jet to slice through the atmosphere with precision. Engineers employed state-of-the-art computational fluid dynamics and rigorous wind tunnel testing to perfect the aerodynamic profile, ensuring that every curve and contour serves a functional purpose. Powering the XB-1 are three General Electric J85 turbojet engines, initially designed for military use. Together, these compact yet powerful engines generate over 12,000 pounds of thrust, driving the jet to supersonic speeds. The engines have been meticulously modified to meet the unique requirements of the XB-1, balancing raw power with reliability. The thrust-to-weight ratio achieved by the XB-1's propulsion system is a benchmark for future high-speed aircraft. Aerodynamic refinement is evident in the XB-1's delta wing configuration. This design provides stability and lift at supersonic speeds while minimizing turbulence. The aircraft's slender nose, designed to reduce shock waves, exemplifies its cutting-edge aerodynamics. These features are the result of thousands of hours of design iterations and testing, ensuring optimal performance at every phase of flight. The cockpit, a technological marvel, replaces traditional windshields with high-resolution cameras. This design innovation enhances visibility for pilots and improves the aircraft's aerodynamic efficiency. Inside, Digital instrumentation provides real-time performance data, enabling precise adjustments and detailed analysis during every test flight. The XB-1 systems represent a leap forward in avionics technology, ensuring its position at the forefront of modern aerospace engineering. Second, Lockheed Martin X59 Quest. The X59 Quest, short for Quiet Supersonic Technology, is the centerpiece of NASA's low-boom flight demonstration program. This initiative aims to revolutionize how we think about supersonic travel by mitigating the disruptive sonic boom. The X-59's mission is as ambitious as it is clear, to demonstrate that supersonic aircraft can operate over land without the explosive noise that has historically grounded them. This groundbreaking project has garnered substantial support, backed by NASA's extensive research and Lockheed Martin's unmatched aerospace expertise. The X-59 is funded through a combination of federal investment and private sector collaboration. At its core is a radical approach to aerodynamics and noise reduction. The aircraft's sleek, elongated fuselage minimizes shockwave interactions, reducing the sonic boom to a faint thump, a noise so subtle it is unlikely to disturb those on the ground. The X-59's nose, stretching an unprecedented 30 feet, plays a crucial role in its quiet performance. This extended design disrupts shockwave formation, dispersing pressure changes more gradually and preventing the sharp, disruptive clap of a traditional sonic boom. The result is what NASA refers to as a sonic thump, a noise akin to the sound of a car door closing, rather than an earth-shaking explosion. The cockpit design further sets the X-59 apart. Unlike conventional aircraft, the X-59 lacks a forward-facing windshield. Instead, pilots rely on an advanced external vision system, which combines high-resolution cameras and augmented reality displays. This innovation not only enhances the aircraft's aerodynamic profile, but also represents a leap forward in cockpit technology, ensuring precise navigation and situational awareness. Propulsion is another critical aspect of the X-59's design. Powered by a single General Electric F414 engine, originally developed for military fighter jets, the aircraft achieves supersonic speeds while maintaining fuel efficiency and reliability. The engine's placement within the fuselage further reduces noise, shielding it from external observers and enhancing the aircraft's stealth-like acoustic profile. Every element of the X-59's design has been meticulously tested and refined. Lockheed Martin and NASA have conducted extensive wind tunnel simulations, computational fluid dynamics analyses, and material stress tests to ensure that the aircraft performs flawlessly under real-world conditions. This relentless focus on engineering precision is what sets the X-59 apart as a flagship of supersonic innovation. The first flight of the X-59 is anticipated to be a historic moment, marking the beginning of a new chapter in supersonic aviation. Test flights will focus on validating the aircraft's acoustic performance, ensuring that its sonic thump is as unobtrusive as predicted. These flights will also provide valuable data on aerodynamics, propulsion, and structural integrity, informing the next generation of supersonic designs. The data gathered during its test flights will be shared with regulatory bodies, including the International Civil Aviation Organization and the Federal Aviation Administration. By demonstrating the feasibility of quiet supersonic travel, the program aims to influence global policies, lifting restrictions that currently prevent supersonic flight over populated areas. This regulatory shift could unlock immense commercial potential. Imagine a future where transcontinental flights are measured in hours rather than days. The ability to fly supersonically over land would redefine long-haul travel, connecting cities and economies with unprecedented speed and efficiency. The X-59's mission is to make this vision a reality, setting the stage for a new class of supersonic airliners. The military implications of the X-59 are equally significant. Quiet supersonic aircraft could revolutionize reconnaissance and rapid deployment operations, allowing missions to be conducted with minimal noise signature. This capability would provide a strategic advantage in scenarios where stealth and speed are paramount. By bridging the gap between commercial and defense applications, the X-59 Quest positions itself as a critical asset in the future of aviation. Third, Spike Aerospace S512. Spike Aerospace, founded in 2012, entered the supersonic arena with a mission to make high-speed air travel more accessible and sustainable. The S512 is designed to meet the demands of business leaders, government officials, and high-net-worth individuals who value time as their most precious resource. Capable of cruising at Mach 1.6, roughly 1,200 miles per hour, the jet will reduce transoceanic flight times by nearly 50%. A trip from New York to London, for example, could take just over 3 hours. The development of the S512 has been supported by a mix of private investments and strategic partnerships. Spike Aerospace has secured funding from venture capital firms and aerospace industry collaborators who recognize the transformative potential of supersonic travel. The Spike S512 is a masterpiece of modern aerospace engineering, meticulously designed to achieve supersonic speeds while maintaining passenger comfort and minimizing environmental impact. The fuselage is crafted from advanced carbon fiber composites. This material not only reduces weight, but also enhances structural integrity, allowing the jet to withstand the stresses of high-speed travel. The fuselage's aerodynamic profile has been refined through extensive computational fluid dynamics simulations and wind tunnel testing, ensuring optimal performance and fuel efficiency. The most striking feature of the S512 is its lack of traditional windows. Instead, the aircraft is equipped with panoramic high-definition screens that display real-time images from external cameras. This innovative approach enhances structural integrity by eliminating the weaknesses introduced by conventional windows, while also offering passengers customizable views and ambient lighting options. The absence of windows reduces drag, contributing to the aircraft's impressive speed and efficiency. The jet's propulsion system is another area of distinction. Spike Aerospace has partnered with leading engine manufacturers to develop a propulsion solution that balances power and efficiency. While specific engine details remain under wraps, the S512's design prioritizes noise reduction and environmental sustainability. By minimizing sonic booms and optimizing fuel consumption, the S512 addresses some of the most significant challenges associated with supersonic flight. Inside the cabin, the S512 offers an experience of unparalleled luxury. The spacious interior can be customized to suit the preferences of its clientele, with configurations ranging from executive meeting spaces to private lounges. Advanced noise-canceling technologies ensure a quiet environment, even at supersonic speeds. Spike Aerospace has completed multiple phases of design validation, including scale model testing and aerodynamic optimization. Another critical focus has been sustainability. Spike Aerospace is committed to integrating sustainable aviation fuel into the S512's operations, reducing its carbon footprint without compromising performance. The use of lightweight materials and efficient engines further contributes to the jet's environmental credentials, ensuring that it aligns with the broader push for greener aviation. Fourth, Venus Aerospace's Stargazer M4. Venus Aerospace, founded in 2020, has taken a bold approach to hypersonic technology, aiming to make the impossible possible. The Stargazer M4 is designed to connect distant parts of the globe in under 2 hours. Imagine traveling from New York to Tokyo in 90 minutes, or deploying critical supplies to remote locations faster than ever thought achievable. This ambitious vision has attracted significant investment from private equity firms, defense contractors, and aerospace innovators. With a funding base exceeding $100 million, Venus Aerospace has secured the resources needed to develop, test, and refine the Stargazer M4's cutting-edge technologies. Every aspect of the Stargazer M4 has been designed to withstand the extreme conditions of hypersonic flight while delivering efficiency and safety. The fuselage of the Stargazer M4 is crafted from next-generation heat-resistant alloys and composite materials, capable of enduring temperatures exceeding 1,000 degrees Celsius. At hypersonic speeds, the heat generated by air friction could melt conventional aircraft materials, but Venus Aerospace's use of cutting-edge thermal management systems ensures the integrity and performance of the aircraft in these extreme conditions. The propulsion system is the Stargazer M4's most revolutionary feature. Venus Aerospace employs a hybrid propulsion design that integrates rocket engines and advanced air-breathing systems. The aircraft uses conventional jet engines for takeoff and transition phases, switching to rocket-based propulsion at hypersonic speeds. This dual-mode system ensures efficient fuel usage and adaptability across various flight regimes. Aerodynamics play a critical role in the Stargazer M4's performance. Its sleek, dart-like design minimizes drag while optimizing lift, enabling the aircraft to achieve and maintain speeds beyond Mach 9. Computational fluid dynamics simulations and high-speed wind tunnel tests have been instrumental in refining the aircraft's shape to reduce shockwave formation and enhance stability at hypersonic velocities. The Stargazer M4 is designed with sustainability in mind, addressing one of the key criticisms of high-speed aviation. Venus Aerospace has committed to integrating sustainable aviation fuels and exploring hydrogen-based propulsion technologies to minimize the aircraft's carbon footprint. Another innovative aspect of the Stargazer M4 is its noise reduction technology. Unlike conventional supersonic and hypersonic aircraft, which produce disruptive sonic booms, the Stargazer M4 incorporates advanced shockwave management systems to mitigate noise. This feature makes the aircraft more viable for overland routes, potentially unlocking a vast array of new destinations. Inside, the Stargazer M4 offers a futuristic cabin environment. Designed for both commercial and military applications, the interior can be configured to accommodate VIP passengers, specialized equipment, or even rapid response teams. Advanced cooling systems and noise-canceling technology ensure passenger comfort even during the intense phases of hypersonic flight. Testing milestones have been a critical focus. Ground-based engine tests and scaled prototype flights have validated the feasibility of the Stargazer M4's propulsion and aerodynamic systems. Full-scale test flights are slated to begin in the coming years, marking a pivotal step toward commercialization. Fifth, space transportation's Jindouyun. Space Transportation, a cutting-edge aerospace company based in China, has developed Jindouyun with the aim of creating a hypersonic vehicle that combines speed, efficiency, and versatility. Its name, which translates to Cloud Rider, reflects the ambition to achieve seamless, near-instantaneous global connectivity. This project has been fueled by substantial investment from both government and private sectors as hypersonic technology becomes a strategic priority for China. With a reported development budget exceeding $300 million, Jindouyun is supported by a network of leading researchers, engineers, and military strategists. The Jindouyun, developed by China's Space Transportation Company, is rewriting the rules of aviation with its unmatched speed and cutting-edge technology. Designed to fly at Mach 4, an astonishing over 3,000 miles per hour, this hypersonic aircraft operates at an altitude of 65,000 feet, twice as high and more than twice as fast as commercial passenger planes. It's not just a breakthrough in aviation, it's a declaration of technological dominance. At the core of the Jindouyun's capabilities is the Jindu 400 ramjet detonation engine, a marvel of innovation. Unlike conventional engines, which rely on steady combustion, the Jindu 400 uses controlled detonations to produce significantly more thrust with less fuel. This engine, measuring about 10 feet in length and 12 inches in diameter, delivers 882 pounds of thrust, making it both compact and efficient. Its hybrid propulsion system allows seamless transitions from subsonic to hypersonic speeds, powering the Jindouyun's ability to achieve Mach 4 with unmatched reliability. The aircraft's aerodynamic design has been fine-tuned for stability and efficiency at extreme speeds. Its elongated fuselage minimizes drag, while advanced simulations and wind tunnel testing have optimized every detail. Built from ultra-heat-resistant alloys and composite materials, the Jindouyun can endure temperatures exceeding 1,400 degrees Celsius generated at hypersonic speeds. These materials, combined with a sophisticated thermal management system, ensure structural integrity and passenger safety. Noise reduction has also been a key focus. At hypersonic speeds, the loud and disruptive sonic boom has historically limited where such aircraft could fly. The Jindouyun, however, employs advanced shockwave management systems to minimize this effect, making it viable for overland routes. This breakthrough not only improves passenger comfort, but also extends its operational range, allowing it to connect more cities than ever before. The Jindouyun's potential extends far beyond commercial aviation. Its speed and adaptability make it a vital asset for military operations. In scenarios where time is critical, the Jindouyun can deploy troops, transport high-priority supplies, or conduct reconnaissance missions with unprecedented efficiency. Operating at altitudes above 65,000 feet, it can evade most traditional air defenses, giving it a strategic advantage in modern warfare. This is only the beginning for space transportation. The successful test flight of a Yunxing prototype in October 2024 marked a major milestone. The company now aims to launch a full-sized hypersonic passenger jet by 2027. Dubbed the Yunxing, this aircraft will feature the Jindu 400 engine, and promise even greater capabilities, such as vertical takeoff and landing, further cementing China's leadership in hypersonic innovation. Imagine traveling from Beijing to New York in just 2 hours, or deploying critical resources to any corner of the globe with unmatched speed. Crazy, yeah? We've seen the rise of Titans, from America's supersonic wonders to China's hypersonic leap forward. The question isn't whether the future of flight will change, it's who will dominate it. And to make this happen, kindly subscribe to the Front Cost channel and smash the thumbs up button below. That would be all for now. Thanks for watching.